So I will talk about photonic devices with reduced indium and gallium content. So as Bertrand said, the only part you cannot do with compatible materials in CMOS fab is the emitters, and we use for this 3.5. And I skip the first one, I go directly to the second one. Yeah. So there is different routes to integrate the 3.5 on the silicon platform. As Bertrand said, you have a molecular bonding of a 3.5 die which has been processed in a 3.5 fab. There is another solution at the bottom right of the slide, which is to directly bond, for example, 3.5 wafers, a piece of wafers, 3.5 piece of wafers like indium phosphide or gallium arsenide, and then you make a Nanoelec of 3.5 on 3.5, which is bonded on silicon. And in this presentation, we will talk more about the direct growth of 3.5 on silicon, which is a more prospective route, which shows some quite interesting result in the last few years. So I will talk now about the 3.5 hetero-epitaxy on standard CMOS silicon substrate. And okay, so there are different challenges for 3.5 direct epitaxy on silicon. Many, at least 3 challenges. The first one is happening when you grow a polar material, gallium arsenide, for example, or indium phosphide, on a non-polar material, silicon. And you see that at the stage of the surface of the substrate, silicon substrate, you can form arsenic bonds or gallium bonds, which form antiphase boundaries. And this challenge has been solved in 2016 when we find a solution to avoid the formation of antiphase boundaries on 300 millimeter silicon 100 substrate used in CMOS fab. The other challenges is the thermal expansion coefficient, which could lead to the formation of cracks if you have to grow two thicker 3.5 layers on silicon. And as I said, as we want to perform or to realize low indium and gallium content materials and devices, we work on thinner devices. And in that case, we are not concerned with cracks formation. And there are still a challenge which has to be solved, which comes from the latest mismatch between the 3.5 and silicon, which induced threading dislocation, which are detrimental structural defects for laser formation. So to do this, there are different ways. The first way is to grow thick buffer layer. It's at the top right of the slide. And people are using dislocation filter, inserting dislocation filter before to grow the NIP junction and the active region. And currently, the best result concerning threading dislocation density is in the 10 to the 7 per square centimeter range. And you can also use selective epitaxy. And in that case, you grow 3.5 in a SiO2 cavity, for example, directly on silicon. And our colleague from IMEC has obtained very interesting result where they show that the dislocation density can be decreased in the 10 to the 6 per square centimeter region. So as we want to be compatible with standard CMOS fab, we use in IRT MOCVD reactors, which is done by Applied Materials. So we grow on 300 millimeter silicon 100 wafers in the clean room, in liquid clean rooms. And what is interesting in this cluster tool is that we have both the MOCVD and the in-situ cleaning of the silicon wafer before epitaxy, which is connected under vacuum on the same tool. So it's really a key point to be able to prepare correctly the silicon surface before the growth of the 3.5. And I will give now some example of results we have obtained. So at the top left, I show a cross-section of gallium arsenide we have grown on silicon 100. So at the interface, perhaps you can see that it's a little bit darker. So it's where the defects are concentrated. And when you go from the bottom to the top of the gallium arsenide materials, you see that the structural defects are less and less present, but still we have threading dislocation which emerge at the surface. On top of this gallium arsenide, we can grow also indium phosphide on top of it to provide an indium phosphide platform. And we have also demonstrated that we can form gallium antimonide on silicon. And all these three types of platform, gallium arsenide, indium phosphide, and gallium antimonide, are free of antiphase boundaries, antiphase domain. But still, we have to work on decreasing the dislocation density. So we use this platform to collaborate with other groups, for example, University College London, and we send some gallium arsenide, sorry, it goes too fast in that case. We say gallium arsenide buffer layers to our colleagues. So we form it on MOCVD, and then they grow dislocation filters and the NIP junction with the emitters, which is done with indium arsenide quantum dots. And it was done, the first results were obtained in 2016, and we were able to obtain a laser emission at 1.3 micron, and the laser is electrically pumped with a density, a threshold current density, which is quite high at this period, 400 amp per square centimeters. And the maximum operating temperatures in continuous mode was 34 degrees C, and the T0 typical temperatures is 32. So then we improve all the different steps. It means the gallium arsenide buffer grown by MOCVD, then the quantum dots growth by MBE, and you see here the top view of AFM pictures of indium arsenide quantum dots. The typical density of the quantum dots is in the 10 to the 10 per square centimeter range. And the fresh threading dislocation density is 3 order of magnitude lower. So the typical PL spectrum you can obtain is represented here with an emission at 1.3 micron, and the full width at half maximum is 28 milli-electron volt. You see also the cross-section of the gallium arsenide buffer plus the dislocation filter. So in that case, you have 1, 2, 3 dislocation filter which have been inserted between the gallium arsenide buffer and the active region of the PIN diode. And you see that the threading dislocation has been considerably reduced to 10 to the 7 per square centimeters. And at the bottom right, you have a cross-section of the indium arsenide quantum dots, which are embedded in the InGaAs layers. So you see that at the scale of this image, there is no threading dislocation with crossing the active region. So with all this optimization, we have recently optimized the laser performances, and you have here the single facet output power in function of the injection current density. So the threshold current density has been reduced in the region of 100 amps per square centimeter at room temperatures. The emission wavelength is always 1.3 microns. The maximum operating temperatures has increased to 65 degrees C at continuous wave operation. So you have a typical cross-section of devices we have done. I just want to mention that other groups are working also on developing this solution, and especially UCSB, which has also obtained very interesting results. And currently, the device lifetime operation is in the order of 10,000 hours. So I just want to mention that another component in the photonic devices is also photodetectors, and we have started some work to try to also form photodetector with direct epitaxy on gallium arsenide, on a germanium buffer on silicon. And this is the typical structures we have drawn. We want to demonstrate and to see if it's possible to make a photodetector with such a high threading dislocation density. And as you see on the IV characteristic, on the dark, it's the black spot and illumination red spot. It's possible to be able to detect the light by using this kind of devices, even if the structural defect density is quite high. So for the next future, what we want to do is to make the complete process by MOCVD in 300 millimeters, and to implement what people call aspect ratio trapping selective epitaxy, which allows to block a part of the dislocation at the sidewall of the silicon dioxide. So we have demonstrated that we could grow gallium arsenide in a cavity on the whole 300 millimeter wafer with a good control of the thickness uniformity and also composition. As you can see at the bottom left, we can integrate quantum wells in selectively epitaxially grown nanoribbons. And at the bottom right, we see also that we want to implement indium arsenide quantum dots directly on a nanoribbon. So the next steps is to make electrically driven devices, which are all grown by MOCVD. So we have shown a development which has been done on free arsenic and free phosphorus hetero-epitaxy on silicon. So we have demonstrated that it's possible to obtain an electrically pumped laser at 1.3 microns. And the next steps is to grow structures for 1.3 and 1.5 emission, all by MOCVD. But we have now to be able to demonstrate that electrically pumped laser could be realized by selective epitaxy, which has never been done. Thank you.
Okay, thank you very much, Thierry. Thank you, Bertrand. Maybe one thing that I can add on the integration of laser is that beyond the integration, what we want to address, of course, is to increase the level of power and to increase the operating temperature. And all and to work on this part, our partner in the program is Almaty Technology. So we use their expertise both in terms of design and on the III-V material.